between two rows? Well, the distance is defined as the number of columns in which they have different values. Okay? So the distance between two rows are just the number of columns in which they have different values. Okay? And in the second phase, using the output of the first phase, the algorithm computes a k-partition of the table. So the k-partition of the table is just a family of subsets of rows. Okay? And these subsets are disjoint, and their union is equal to the original table. And if each subset contains at least k rows, then we call this family a k-partition of the table. And in the third phase, the algorithms computes a k-anonymized table using the output of the second phase. So here, to build a protocol, privacy-preserving protocol for this algorithm, we notice that the second phase is pretty trivial because using the output of the first phase, the miner can simply do it locally, and there is no additional privacy, additional information leak. So this is easy. Then all we need is a protocol for the first phase and a protocol for the third phase. Okay, so now let's build a protocol for the first phase. So consider two rows, the ith row and the I prime row, and also a column, which is a jth column. Okay. Now we define a variable called sigma sub j super I prime, which is equal to 1 if the two rows have the same value in this column. And it is equal to a uniformly random value otherwise. Okay? Given this definition, we can easily see the distance between the ith and the I prime row is exactly equal to the number of ones in this set. Sigma sub j super I prime for I equals 1 through m.
What is the range you are picking uniform random from?
Well, I intentionally hide this range because we need some additional property of this range later. So I will make it clear later.
Just roughly how many values are in there? Infinite?
Oh, no, finite, but it needs to be exponentially many. Okay, so given this relationship, we have reduced the problem of computing the distance to the problem of computing this variable sigma. So here, this answers your question. In what kind of range we pick this element? We have to work in a prime order cyclic group because only in this situation we have the additional property we need here. Okay? So in this slide, we explain how we compute this new variable sigma. So we further observe that in a prime order cyclic group, we have this additional relationship, which is the sigma sub j super I prime equals the jth quasi-id of the ith row over the jth quasi-id of the I prime row raised to a uniformly random exponent. So this exponent is picked uniformly random from the set 1 1 through Q, where Q is the cardinality of the group. Okay. So now, so you might wonder why this is true. Observe that if these two entries are equal, then we have 1 in this. We have 1 inside, and of course no matter what kind of exponent we pick, the sigma is always equal to 1 in this case. So we have 1 when these two entries are equal, and we have a uniformly random element if they are not equal.
So it's a division, modular division? You are doing a division in the group?
Yes. So now we have further reduced the problem to computing the quotient of two entries. Okay, so how can we compute the quotient? So this is pretty simple. We use a multiplicative homomorphic encryption scheme. So by saying an encryption scheme is multiplicative homomorphic, we mean taking two encryptions, you can easily compute an encryption of the product of their clear text. Okay, so you don't need to do multiplication and division on the clear text. You can directly do it on the encryptions. So now, given this encryption scheme, the customers can the miner can compute the encryption of the quotient, and the customers can jointly help the miner to decrypt the quotient using an existing technique called threshold decryption, which was invented by Desmet and Franco in 1989. So good. We are done with phase 1.
You go back to where phase 1 is described.
Oh, yeah, sure. So we are done with phase 1. So we have a series of reductions from computing distances to computing sigma, and from computing sigma to computing quotient, and then we show how to computing quotient. Okay? Now, we need a protocol for phase 3. Phase 3, computing the k-Anonymized table from k-Partition. Recall, a k-Partition is just a partition of the table into subsets of rows, and each subset contains at least k rows. Okay? So in the MW algorithm, taking the output of phase 2, which is a k-partition, all we need to do is the following. If all rows in a subset agree on a quasi-id, no operation is needed. Otherwise, replace the values of this quasi-id with star. That's it. So this is a very, very simple operation. So now the question is, how can we do this in a privacy-preserving way? Because we won't have all these, we won't have the outputs of phase 2 in clear text to the miner. The miner only has encryptions of the k-partition. So to do this, we again have an observation. So